Welcome to our tutorial on solving a furrow irrigation system problem. Today, we'll work through a practical engineering problem to determine the optimal inflow time for a furrow irrigation system. Let's start by looking at our problem statement. A 50 meter by 50 meter furrow irrigation system was designed with the following conditions. Soil water holding capacity equals 180 millimeters per meter. Root zone depth equals 300 millimeters, management allowable depletion or MAD equals 50%, application efficiency equals 70%, and furrow spacing equals 75 centimeters. We're also given an empirical infiltration law, where F sub n equals 1.4 times T sub n raised to the power of 0.77. The question asks, assuming that the advance time is 1/3 of the net opportunity time, what should the inflow time be? Before we dive into the calculations, let's visualize what a furrow irrigation system looks like. Here we have a field with dimensions 50 meters by 50 meters. The field is divided into furrows, which are small, parallel channels that help distribute water across the field. The furrows are spaced 75 centimeters apart, as specified in our problem. Water flows into these furrows from one end and gradually advances along the length of the furrow. Below the surface, we have the root zone with a depth of 300 millimeters, where plants absorb water. The key challenge in furrow irrigation is determining how long to allow water to flow into the furrows to ensure proper infiltration without excessive waste. Now, let's solve this problem step by step. Step 1. We need to compute the net depth of water required, which we'll call Z sub n. First, we calculate the available water in the root zone by multiplying the soil water holding capacity by the root zone depth. That's 180 millimeters per meter times 0.3 meters, which equals 54 millimeters of available water. Next, we apply the management allowable depletion, or MAD, which is 50%. This tells us how much of the available water we allow to be depleted before irrigation. So, the net depth Z sub n equals 0.5 times 54 millimeters, which equals 27 millimeters. This is the amount of water we need to apply to the root zone. Step 2. We need to convert the net depth to gross depth using the application efficiency. The gross depth, Z sub g, equals the net depth divided by the application efficiency. Application efficiency accounts for water losses during irrigation. So Z sub g equals 27 millimeters divided by 0.7, which equals 38.57 millimeters. This means we need to apply approximately 38.6 millimeters of water to ensure that 27 millimeters actually reaches the root zone. The difference represents water lost due to inefficiencies in the system. Step 3. We need to determine the depth lost to infiltration. The depth lost to infiltration, Z sub infiltration, equals the gross depth minus the net depth. That's 38.57 millimeters minus 27 millimeters, which equals 11.57 millimeters. This represents the amount of water that will infiltrate beyond the root zone. Step 4. We need to calculate the cumulative infiltration per unit length of furrow. The cumulative infiltration per unit length, F sub n, equals the depth lost to infiltration multiplied by the furrow spacing. That's 11.57 millimeters times 0.75 meters, which equals 8.678 millimeters. This represents the volume of water per unit length of furrow that infiltrates beyond the root zone. Step 5. Now we can use the empirical infiltration law to solve for the net opportunity time. Recall that our infiltration law is F sub n equals 1.4 times T sub n raised to the power of 0.77. where F sub n is in millimeters and T sub n is in hours. We need to solve for T sub n, the net opportunity time. Rearranging the formula, we get T sub n equals the quantity F sub n divided by 1.4, raised to the power of 1 divided by 0.77. Substituting our value for F sub n, we get T sub n equals the quantity 8.678 divided by 1.4, raised to the power of 1 divided by 0.77, which approximately equals 1.055 hours or 63.3 minutes. The net opportunity time is the total time water needs to be in contact with the soil to achieve the desired infiltration depth. Step 6. Finally, we can calculate the advance time and the inflow time. The problem states that the advance time is 1/3 of the net opportunity time. So the advance time equals 1/3 times 63.3 minutes, which equals 21.1 minutes. The advance time is how long it takes for water to reach the end of the furrow from the start. The inflow time, which is what we're asked to find, is the remainder of the net opportunity time. So the inflow time equals the net opportunity time minus the advance time, or equivalently, 2/3 of the net opportunity time. That's 2/3 times 63.3 minutes, which equals 42.2 minutes. Therefore, the inflow or cutoff time should be about 42 minutes. This is how long water should flow into the furrows to ensure proper irrigation of the field. Let's summarize what we've learned. To solve this furrow irrigation problem, we first calculated the net depth of water required based on soil properties and management decisions. Second, converted this to gross depth using the application efficiency. Third, determined the depth loss to infiltration. Fourth, calculated the cumulative infiltration per unit length of furrow. Fifth, used the empirical infiltration law to find the net opportunity time. Finally, calculated the advance time and inflow time. This approach allows us to precisely determine the optimal inflow time for irrigation systems, ensuring efficient water use and proper crop hydration. The inflow time of 42 minutes will provide the right amount of water to the root zone while minimizing losses.